In this video, we're going to talk about change of basis in Rn. In a change of basis, coordinates of a vector relative to one basis, b, are given and used to find coordinates relative to another basis, b'. Using multiplication, the matrix P changes a coordinate matrix relative to b' into a coordinate matrix relative to b, and is called the transition matrix. We call this a change of basis from b' to b, represented as P times the coordinate matrix of x relative to b' is equal to the coordinate matrix of x relative to b. Similarly, a change of basis from b to b' is given by the coordinate matrix of x relative to b' is equal to P inverse times the coordinate matrix of x relative to b. Let's take a deeper look at these concepts with the following example. Find the transition matrix from b to b'. We'll find the transition matrix from b' to b. We will verify that these matrices are inverses of one another. And then we will find the coordinate matrix x relative to b when given the coordinate matrix of x relative to b'. So let's suppose that b is equal to 1, 3, and negative 2, 2. Let's suppose that b' is equal to negative 12, 0, negative 4, 4. And let's also suppose that we're given the coordinate matrix of x relative to b', which is a 2 by 1 matrix with entries negative 1 and positive 3. To find our transition matrix from b to b', we know that b to b', if we have this, then we have the identity matrix, to P inverse. We'll set up our b to b', which, coming from our given information, is 1, negative 2, and 3, negative 2. B' is negative 12, negative 4, 0, and 4. Let me go back and make one adjustment. Since our transition matrix is from b to b', although it seems counterintuitive, we actually need to put our matrix b' first. So we have negative 12, negative 4, 0, 4, and for matrix B, 1, negative 2, 3, negative 2. As you can see, this is a common place to make a mistake. So remember, transitioning from B to B' means when we set up our matrix, we put B' first and then B. Now we simply conduct row operations, or we can use our graphing calculator to find the reduced row echelon form. I'll use the graphing calculator. And my result is 1, 0, 0, 1, negative 1/3, positive 1/3, 3/4, and negative 1/2. This matrix is our P inverse. If we want to find the transition matrix from B prime to B, then when we set up our matrix, we put values for B first. So we have 1, negative 2, 3, negative 2, and then our B prime, negative 12, negative 4, 0, and 4. Again, we put this into reduced row echelon form. I'll use my graphing calculator for this. And if you're not familiar with how to use the graphing calculator, using a TI-84, you would type the following commands. Second, matrix, highlight edit, and I would just select matrix A. Then you'll have to set the matrix size, which this is 2 rows by 4 columns, so it's a 2 by 4. Enter values row by row. Then you'll go to second, quit, and back into second, matrix. This time, highlight math, scroll down to select RREF, then you'll type second, matrix, and press enter to select option A, and enter. Following this process will give you the result 1, 0, 0, 1, our identity matrix, and 6, 4, 9, 4, which gives us our matrix P. Now we wish to verify that P and P inverse are inverses of one another. By setting it up as follows: P times P inverse is equal to our matrix P times our matrix P inverse we can multiply these matrices together and the result will be the identity matrix. Therefore, matrices are inverses. I'm assuming by now that most of you know how to multiply two matrices. If you did want to use a graphing utility, you would simply enter matrix A as P and let P inverse be matrix B. Then you would type second matrix A times second matrix B and it would yield this result. Lastly, we'd like to find the coordinate matrix of x relative to b when we are given the coordinate matrix of x relative to b prime. Let's recall that we were given some information on the coordinate matrix of x relative to b, and that's the information we'll use now. The coordinate matrix of x relative to b prime is equal to negative 1, 3, as a 2 by 1 matrix. And so by definition, the coordinate matrix of x relative to b is equal to p times the coordinate matrix of x relative to b prime, which is the 2 by 2 matrix 6, 4, 9, 4, which we found in a previous step, multiplied with the coordinate matrix of x relative to b prime, again using standard matrix multiplication procedures. We'll find that the coordinate matrix of x relative to b is equal to the 2 by 1 matrix 6, 3. This concludes our example. I hope you found it helpful, and we'll see you next time.